Alright, this is limits and continuity number 2, limit solving strategies. So this is going to be kind of an overview of all of the limit solving strategies you need to know, the techniques, and where you use them. The first one, and by far the easiest, and the one you should always try before you try any other one, is just direct substitution. So whatever the limit is approaching in the x, so x is approaching 2, just plug that into the function and see what happens. So in this case, it actually works out. Usually it doesn't. But if we plug in a 2 in for x, we get 4 over 1, which is 4. So our second technique is factoring. This comes in handy when you have a polynomial divided by a polynomial. So basically, just behind this, you factor the top and you factor the bottom, and then you try and cancel out the factors, and then see if you can substitute in and if it works out. So what I tried here first was actually substitution, because you should always try that first, much easier than anything else. So if you plug in a 2 here, it's 4 minus 5 times 2 is 10. 4 minus 10 plus 6 is 0, and then 4 minus 4 is 0. So we have a 0 over 0, so indeterminate, we have to try something else. The other thing I'd like to say with having a 0 and a 0, we plugged in a 2 here and got 0. We plugged in a 2 here and also got 0. So what that means is that 2 is a 0 for both of these polynomials. So let's just look at this. We plugged in 2 and we got a 0. What that means is that x minus 2 is a factor of that, because if you plug in 2 to this, you get 0, and we got a 0. Like, saying that something is a 0 literally means you plug in that number and you should get 0, and that's what happened for both this one and this one. So in theory, we should have x minus 2 being able to be factored out of both this expression and this expression. And that only works when you have like factorable polynomials, but keep that in the back of your head. When you get 0 over 0, you should get a factor of whatever your x is approaching from both the top and the bottom. So now let's try and factor this. So if we look at the numerator, and we already know that this is going to come out, so I guess we can write that first. If we look at the numerator, this factors pretty easily into, so we have minus 2 minus 3, that adds up to negative 5, and a minus 2 times a minus 3 also multiplies to 6. So there's our factored expression up there, and then this one, even easier, just x minus 2 and x plus 2. You've seen that thousands of times, I'm sure. But now we can factor both of those out, or we can cancel both of those out, and our hypothesis, if you will, worked, of taking out an x minus 2. But now we can rewrite this, the limit as x approaches 2 of x minus 3 over x plus 2, and now we can actually plug in the 2, and our final answer is negative 1/4. Next strategy is multiplying by the conjugate. So with factoring, it worked when we had a polynomial over a polynomial. Conjugates usually come into play when you have radicals and you want to get rid of them. So we're going to try and get rid of this radical by multiplying by the conjugate of this. But before we even get to that, we want to check if the substitution works. So if we plug in a 3, I won't write it out, but if we plug in a 3, 3 plus 1 is 4, the square root of 4 is 2, 2 minus 2 is 0. Plug in a 3 here, 3 minus 3 is 0, so we have a 0 over 0. If you remember up here, that kind of gave us some help, but in this case it really doesn't, because factoring out an x minus 3 from this is probably a lot harder than just multiplying by the conjugate, which we'll do now. So the conjugate of this, just switch the sign in the middle, keep all the terms the same. We're going to multiply this whole fraction expression by 1, but it's going to be a special type of 1 called that. We're just dividing that by the same thing, so we're not really changing the expression. We're just making it look better so that we can actually deal with it a little bit easier. So now we just FOIL the top and the bottom. We set this up in a way so that we could cancel the inner terms. So if we FOIL this, we're just multiplying this times this, and that turns into x plus 1 because it's the square root times the square root. So we have x plus 1 in the numerator so far, and then we have a plus 2 times that and a minus 2 times that. 2 minus 2 is 0, they cancel, and then a minus 4. That is a strange minus, but... And then in the denominator, we'll just keep it separate for the time being. So I just rewrote this whole thing. I accidentally put the square root over the plus 2. That's not supposed to be there. We just wrote that down there. But anyway, now we can have 1 minus 4, and that turns into a negative 3. And then in the numerator now we'll have x minus 3, and we'll actually be able to cancel that out. So now we can divide out the x minus 3 from both the top and the bottom, and then we're just left with this in the bottom. We can directly substitute now. So if you put in a 3 for the x, 2 plus 2 is 4, 1 over 4. This doesn't turn into 0, right? This is, if you want to write it as that, x minus 3 times 1. When you're dividing out a term, it doesn't go to 0, so this limit wouldn't be 0. It would be 1 on the top and 4 on the bottom. And then technique number 4 is using trig identities. So if this is our limit expression, obviously you'll use the trig identities more when you see trig stuff. None of this stuff had sines or cosines, so you were good there. But up here, I've actually written basically all of the trig identities you really need to know. So it's just the double angle for sine. Sine of 2x equals 2 sine x cosine x. The double angle for cosine and all of its various forms. And then the sine squared plus cosine squared equals 1. And then these new ones that you probably didn't see before this fall. The limit as x approaches 0 of sine x over x and infinity of sine x over x. But now we just use these and apply it to not just this, but 99% of all the limit expressions you'll get can be figured out with some combination of these. But anyway, this one's not too bad. So if we notice this double angle for sine, let's substitute that in. So the limit as x approaches 0 of sine x, and now instead of sine of 2x, we can write it as 2 sine x cosine x. I guess I forgot to, but the substitution thing, plugging in a 0, sine of 0 is 0, sine of 2 times 0 is 0, 0 over 0. So we were going to have to do this anyway. Sorry, I forgot that. But back to this. We have 2 sine x cosine x and a sine x on the top. Those go away, and now we can actually plug in our limits. So x approaches 0 of, now we have 1 over 2 cosine x, and cosine of 0 works out to be 1. So this whole limit is equal to 1/2. The last strategy, if you can even call it that, is reliable, aka guessing. So we have this expression here. Say I'm taking a test and I have no idea what to do. If I'm in that tough of a spot, I would see what my limit was approaching, pick a number extremely close to that, plug it in for each t, work it out painfully by hand, and then have an answer, see what it's close to, and make an educated guess. So I'd plug in like 1.0001, and then work everything out by hand, see what it's close to, and then hopefully that would be the answer. Now, if you have a calculator, this would be a lot easier by just graphing the expression that you have, and then visually looking at, zooming in at t equals 1 and seeing what the y values are approaching, or using your table function. Now, if you get some weird string of decimals, then that might indicate that you had like a square root, or you were supposed to have a square root in your answer, or a pi in your answer. So you might have to take the L at that point, but try this in the worst case scenario. If you really have to, I guess, there you go. So that was it. That was pretty quick. This was just an overview of where and when you use the common limit solving strategies or techniques. In the future, you'll actually learn one called L'Hopital's rule, where you can like take the derivative of the numerator and denominator. But this is just the introductory stuff. In the next video, we'll go over the intermediate value theorem. So I'll see you in the next one.